Let's now consider what happens if our 2-point sources down here are out of phase. So instead of oscillating together in sync, they are 180 degrees out of phase, pi out of phase. What are the angles of constructive interference in this case? Well, we get constructive interference now when the path difference is an integer number of wavelengths plus half a wavelength. And the extra half wavelength in one of these paths will give us back the constructive interference. So we can use all of the things we did in the previous derivation. We got the construction here for R1 and R2. And now the difference between R1 and R2, instead of being m times lambda, is m plus a half times lambda. So the difference is this plus a half, this extra half wavelength, that gives us back the constructive interference in the case where these two sources are now out of phase. And we follow that previous derivation through, make the approximation of these two sources being close together compared to the distance over here, and we end up with this diffraction equation for the 2-point sources out of phase. Instead of being m lambda is d sine theta, it's m plus a half times lambda is approximately equal to d sine theta. You could also imagine doing any number of different derivations for different phases between these sources. If they were pi on 2 out of phase, so 90 degrees out of phase, then you can ask what difference in lengths here between R1 and R2 do you need to get back constructive interference. You need to add an extra quarter of a wavelength somewhere, in other words, to give you that pi on 2 phase shift. You could also ask questions about what angle do you get destructive interference. Now, as it turns out, if we have 2-point sources in phase, then the derivation for destructive interference looks exactly like this. So this is actually the equation for destructive interference between two in-phase sources. Those angles are the same as the constructive interference for two out-of-phase sources. So either way, it's just a simple geometric construction, looking at the difference in the distances here and then asking the question about whether we get constructive or destructive interference depending on what you're looking for. Now let's think about having 2-point sources and we bring them very, very close together and see what happens to the radiation pattern, the pattern of the waves, as we bring them together. This is the case for 2-point sources that are in phase, and we see as we bring them very, very close together, the limit, as the separation here tends towards 0, is that we get a point source. So as they get closer and closer together, the destructive interference lines, that's these destructive interference lines here, go away, and at some point the 2-point sources basically merge together and we get a single point source, and this radially or spherically symmetric wave pattern coming out of the middle. So the 2-point sources merge into a single point source. What about the case where we have sources that are out of phase? What happens then? Well, now, in this case, what I've drawn here, these black lines, are the first order interference fringes. So that'd be the case where m is equal to plus and minus 1 in our diffraction equation. And as we get closer and closer together, as soon as we get to a distance of less than half a wavelength, so we hit half a wavelength separation here, as soon as we get past that point there, we can no longer define a first order interference because the sine function, the inverse sine function in our diffraction equation becomes greater than 1, and we end up with this stable pattern of radiation where in this vertical direction here we have destructive interference, and out the sides here we have constructive interference. And this radiation pattern here, this pattern of amplitudes as we go around the circle here, this is known as the dipole radiation pattern. And it's the pattern you get when you have out-of-phase sources that are equal to or less than half a wavelength difference from each other. It's the kind of pattern you get from radiation from an atom, for example, when you have an electron oscillating in an atom, even in a quantum dipole, you get a radiation pattern that looks like this. So you may hear the term dipole radiation pattern in your later studies. This is where it comes from, and this is what it looks like.